So thanks again. Thank you for the invitation to speak. Although I have to tell you, Matthias, I wish I were speaking live because I love to give talks at a blackboard, but now I'm sitting at my desk, which is not so much fun. And as you know, these are really depressing times. I'm going to paraphrase Woody Allen. He said, "More than any time in history, mankind stands at a crossroads. One path leads to despair and utter hopelessness, the other to total extinction. Let us pray we have the wisdom to choose correctly." So with those unpleasant thoughts, I'm going to begin. So the theme of this talk is that mathematicians find it enlightening to extend the real number system to the complex number system. And this helps us to understand the real number system better. And in this talk, what I'm going to do is to extend conventional real physics to complex physics. And by doing so, I'm going to show you that we can understand quantization better. We can explain the divergence of perturbation theory. We can generate new PT-symmetric quantum theories. We can tame instabilities and much, much, much more. But that maybe is for a talk some other time. So the outline is that this talk is organized in 3 parts. Here they are. And I hope you find it interesting. Okay, so as you know, conventional real numbers are used to describe standard real-world things like election results, like IQ test results, okay, like money. And here is an example of a real measure of money, just in case you need one. But complex mathematics is very powerful, and it can explain all sorts of things about real numbers, okay? It can explain the convergence of real Taylor series. It determines the asymptotic behavior of real integrals. It enables us to sum real divergent series. It explains real functions like the square root function and much more, which we could talk about some other time. Okay, so here's a very simple example. Take the function 1 over 1 plus x to the 4th. Okay, and here is its Taylor series. And if you look at a plot of the function, it's nice and smooth, and yet the Taylor series has a radius of convergence or divergence at plus or minus 1, even though you don't see anything happening in the curve at plus or minus 1. Why is this? And as you all know, the answer is that there are singularities in the complex plane that cause the Taylor series to diverge, even though you cannot see them on the real axis. And just in case you haven't yet studied the complex plane, here are some examples. This particular plane over here works very, very well, except it has one problem. The passengers ride over here, but the toilets are over here. But apart from that, it's a great design for a plane. So here's something a little more subtle. Consider this real integral over here. This is an integral from -1 to 1, and everything about the integral is real. And we can ask, how does the function I of x behave when x is large, say large and positive? And here's the answer. As x goes to plus infinity, I of x behaves like, has a simple leading asymptotic behavior, behaves exponentially times an algebraic correction. Okay, now you could argue that for large x, this exponential here is clearly vanishing very rapidly as t moves away from the origin. So therefore, it must be that the contribution to this integral is localized near t equals 0. Otherwise, this becomes exponentially small and it becomes irrelevant, right? So if it only contributes when t is near 0, we could set t equal to 0 in this cosine function, or if you want to be a little bit more careful, you could throw away t cubed compared with t. And then you can do this integral exactly. And if you follow that recipe, you get the wrong answer. Because in fact, the contribution to this integral is not localized at 0. This is a very, very difficult and subtle integral. And using Laplace's method type ideas, which I was explaining just a moment ago, that doesn't work. So what do? What you have to do is extend the integral into the complex plane. And instead of integrating from -1 to 1, you have to follow a steepest descent path. Okay, and a steepest descent path from -1 goes off to infinity in this direction. And then you come back from infinity, you pass through a saddle point over here on the positive imaginary axis, and you go back off to infinity, and then you go from infinity back down to 1. In other words, we have deformed the finite contour from -1 to 1 into a complex contour that consists of 3 infinite parts. Okay, 3 infinite parts. And now the contribution is localized at this saddle point over here, and you can obtain this asymptotic result very easily. But here's a challenge to you. Without using complex variables, it's virtually impossible to deduce this result. This result is a very, very difficult and subtle result. And if you can derive this result using real variable analysis alone, that's very impressive. And I think you should probably publish it. Okay, so what about divergent series? These are 4 examples of divergent series. And I will show you what the sum of these series is. Here's the answer: 1/2, -1, -1/2, -1/12. You can obtain the sum of these series by using real variable techniques. But if you use but if you need to sum these 2 series, real variable techniques are not powerful enough, and you need to use complex variable techniques to obtain these results. And by the way, these results are not, this is just mathematical, this is not just mathematical fun and games. These types of series arise when you do sums over modes, normal modes. And these are physically testable results. I mean, these can be verified in a laboratory. Okay, so what about making sense of real functions? The square root function is a nice simple function, but in fact it's very confusing because there are 2 answers, and one function cannot have 2 answers, at least you would think. So how do you make sense of the fact that there are 2 answers? And the answer is that a square root function is defined on a Riemann surface, okay? And the Riemann surface for the square root function is a 2-sheeted surface. It consists of 2 complex planes cut over here, this is a cut, and glued together, okay? And the reason why there are 2 possible answers is that on one complex plane, you get one answer, and on the other complex plane, you get another answer. And the combination of the 2 planes is the Riemann surface. And in fact, if you go around, if you take a continuous trip around the Riemann surface, you come back to where you started. If you start here on the lower plane and you go around, you wind up at the upper plane. And if you continue going around, you go back down to the lower plane. And if you come around again, you come back to where you started. So the surface is like a Mobius strip. And if you go around twice, you return back to your starting point. Okay, so these are some things that remain the same when you go around twice. For example, a Mobius strip stake here, or an electron. Here you have, if you go around an electron 360 degrees, what you see is not the same electron. But if you go around a second time, you see the electron you started out with. Okay. Okay, so complex numbers and complex variables are already used, of course, as you know, in modern physics. The complex number I appears in the Heisenberg algebra here. okay? It also appears in the Schrodinger equation here. Here's I, okay? And you can see that since P changes sign under time reversal, you know that I, to compensate for it, must also change sign under time reversal, okay? And in the Schrodinger equation, again, you can see that because of time reversal invariance, if I changes sign, T changes sign, okay? And it was Wigner who pointed out that time reversal corresponds to complex conjugation. Okay, and in school, you learn that quantum mechanics, in quantum mechanics, a particle in a potential well has quantized energy levels, okay? And you also learn that going from one level to another is a discrete process, and some people call it a quantum leap, okay? But complex variables gives you a deeper understanding of quantization. And let me just give you a simple description. So I want you to imagine a two-state system having energies A and B. He cannot imagine it, but you can. So here's a 2x2 Hamiltonian, and there are two energies, A and B. But now what I'm going to do is couple the states with a coupling constant G, okay? And then I'm going to ask, what are the energy levels of this 2x2 Hamiltonian? So I take the determinant of H minus I times E, okay? And when I take the determinant, I get this secular equation here, and I find the roots of the secular equation, and here they are. And what you see is that there are square root singularities in the complex coupling constant plane, the G plane, at these 2 points, G equals plus or minus A minus B over 2 times I, okay? These are actually called Bender-Wu singularities because they arose in our studies a long time ago of the anharmonic oscillator. And so what you see is that the energy function is a smooth function of G that is defined on a two-sheeted Riemann surface. Okay, why are there two energy levels? Because there are two sheets in the Riemann surface. Notice that on this complex G surface, the quantum energy levels are not discrete. And what you see also is that quantization is topological. The quantized energy levels correspond to the discrete sheets in a Riemann surface. So when you say that the energy levels are discrete, what you really mean is that the sheets in the Riemann surface, the sheets that combine to make the Riemann surface, are discrete. And by the way, these singularities in the Riemann surface explain the divergence of perturbation series. And by the way, furthermore, complex variable techniques can be used to sum the divergent series and obtain a finite result. Okay, so in general, you can imagine a parking garage, and unfortunately he can't, but you can. And in a system that has many energy levels, that corresponds, if you extend that system into the complex domain, it corresponds to a multi-sheeted Riemann surface where the energy levels correspond to the sheets in the Riemann surface. The reason that you think that the energy levels are discrete is that you live in the real world. And indeed, if you take a slice of this parking lot along the real axis here, what you see is discrete energy levels, okay? But that's only on the real axis. In fact, there is a continuous path from all energy levels to all other energy levels, okay? So unlike what is taught in conventional quantum theory courses, all energy levels smoothly deform into one another under analytic continuation. So this is not just mathematics, this is physics, okay? And here are three very recent papers in which experiments have been done where they have analytically continued the energy levels in a multi-level quantum system into one another. The first paper here called PT-symmetry and spontaneous symmetry breaking in a microwave billiard. What was done here was to take a microwave cavity that has many modes and analytically continue one into the other, one mode into another by varying the parameters, of the theory, okay, which can be done continuously. And here are two more recent papers in Nature, back-to-back papers in Nature, where the same thing was done in real time, where you actually have dials and you twiddle the dials and you can actually go from one energy level to another. And what I want you to note here is the term PT-symmetry, because that is in the title of this talk, okay? And so note this term PT-symmetry. PT-symmetric quantum mechanics consists of extending quantum mechanics into the complex domain. And that's what we've been talking about all along. And what I'm gonna, a very important point here is that if you respect PT-symmetry, the eigenvalues can remain real and unitarity can be preserved, even though the Hamiltonian is not Hermitian. So here's a picture of a PT reflection, which is a reflection in both space and time. Okay, so we're going to be discussing Hamiltonians that are PT invariant, that is invariant under a simultaneous reflection of space and time, P and T. Okay, so the origin of PT symmetry is kind of straightforward. This is a picture of the Lorentz group. And as you all know, the Lorentz group consists of all real 4x4 matrices. And these matrices map the vector, the four vector x, y, z, and t into x prime, y prime, z prime, and t prime. Okay, and the group of the, and of course, these matrices are required to preserve the value of x mu, that is x squared plus y squared plus z squared minus t squared. Okay, so that has to be preserved. And these 4x4 matrices do so. The Lorentz group consists of 4 disconnected continuous parts. The first part is the proper orthogonal Lorentz group. Okay, and then the second part consists of all the elements of the proper orthogonal Lorentz group multiplied by t. The third part is all of those elements multiplied by p. And the fourth part is all those elements multiplied by pt. Now, if you extend the real 4x4 matrices to the complex 4x4 matrices, you get the complex Lorentz group, and that consists of 2 disconnected parts. That is, you can start with one of the elements in this part of the group and continuously go, if you are talking about the complex Lorentz group, into this. And if you start here, there is a continuous pathway to here. So these 2 parts join, and these 2 parts of the Lorentz group join. Okay, now you know that the world is not time reversal invariant or parity invariant. Okay, but this is the beginning of the proof of the CPT theorem. Okay, and PT combined is a very nice symmetry. Okay, and you can see that already. Okay, so here is an early example of a PT-symmetric Hamiltonian, p squared plus ix cubed. This Hamiltonian is obviously not Hermitian, but it has real eigenvalues. And this Hamiltonian arises as a one-dimensional model of the Liang edge singularity. It also arises in Region field theory, and I won't go into the background of this, but this is a very simple example. Although I must say, when I first saw this Hamiltonian, my initial reaction, because I have a conventional training in physics, was, for me, I said, the way I see it, this theory is crazy because the Hamiltonian is not Hermitian. But you can see that it is invariant under PT because under parity, space reflection, x goes to minus x, p goes to minus p, but under time reversal, x goes to x, p goes to minus p, but I goes to minus I. And therefore, ix cubed is invariant under a PT reflection, even though it is not Hermitian. Okay, now that's just one example of a very big continuous class of Hamiltonians. Consider the Hamiltonians p squared plus x squared times ix to the epsilon, where epsilon is real. Okay, and under a PT reflection, I changes sign and x changes sign. So this Hamiltonian is PT invariant. And if you calculate the eigenvalues of this Hamiltonian, so here they are discrete. The horizontal axis is the value of epsilon. The energy eigenvalues are plotted on the y-axis. And here's the ground state, the next level, and so on. And you notice that all of the eigenvalues are real. Okay, this is not a Hermitian Hamiltonian, but its eigenvalues are real. And the first Hamiltonian I showed you is the cubic special case where epsilon is equal to 1. An interesting special case is the quartic Hamiltonian, p squared minus x to the 4. And notice that it has real, if you take epsilon equals 2, it has real positive eigenvalues, even though this is an upside down potential, which we will talk about. Another interesting special case is the sextic case, where epsilon equals 4, and here we have p squared plus x to the 6th. Okay, if you want to see a proof of the spectral reality, you can read these papers. They're pretty long and detailed, but this is a rigorous proof showing that the eigenvalues of these Hamiltonians are all real when epsilon is positive. Okay, so here's what you should remember. PT-symmetric Hamiltonians are complex deformations of Hermitian Hamiltonians. So the idea is that you begin with a Hermitian Hamiltonian and you introduce a complex deformation. That is, you put in a deformation parameter epsilon, okay? And so a very simple example is to start with just the harmonic oscillator, put in a deformation of the form Ix times epsilon, okay, and Ix, remember, is PT invariant. So this Hamiltonian is no longer Hermitian, but if you solve the corresponding Schrödinger equation with the usual boundary condition, what you find is that the eigenvalues are all real. Okay, this is a very simple case. But in fact, the picture that I showed you is generic, and here are some very fancy examples. We could take the Hermitian Hamiltonian p squared plus x to the 4 times ix to the epsilon, and the picture looks exactly the same. All these eigenvalues are real and positive and discrete when epsilon is a positive real number. Here's another example, p to the 4 plus x squared, a Hermitian Hamiltonian multiplied by ix to the epsilon. And again, the eigenvalues are all real, positive, and discrete. Here's a very fancy one, okay? And again, the eigenvalues are all strictly real, positive, and discrete when epsilon is positive. Okay, and if you want to read something very non-technical and simple about PT-symmetry, here's an article that's only about 3 pages long. It appeared in 2016. And the article is called PT-symmetry and Quantum Physics. You can download it and read it in 5 minutes. In the article is a very nice picture that I took. I visited the lab where they did the first experiment on a PT-symmetric system, and this is the experiment. It's an optical experiment involving lasers, and this is really a beautiful experiment, and it was the beginning of the experimental work on PT-symmetric physical systems. Okay, I was really happy with this cartoon that appeared in Nature Physics. It appeared in 2015. The title of this cartoon is The Top 10 Physics Discoveries of the Last 10 Years, which is really great. The article is, the cartoon is very funny because every single one is a pun of some sort, like the Higgs bison here. But I was very happy to see that there is a discussion of parity-time-symmetry and optics. They left off the I in parity-time-symmetry and optics. That made me very happy. Okay, so let me give you an example of how complex variables is crucial in understanding PT-symmetric quantum mechanics. And what I'm going to talk about is the stability of upside-down potentials. I said before that the PT-symmetric Hamiltonian p squared minus x to the 4 has a positive real spectrum. How can that be? This is an upside-down potential. It must be unstable. Okay, it certainly looks unstable on the real axis, but you're going to see that complex variables explains why such a potential has quantum bound states. Okay, so to explain, we first study the simple classical harmonic motion in the complex domain. Okay, so let's remember what they teach you in first year physics. You study the classical harmonic oscillator. This is not quantum, this is classical. For first year undergraduate physics, what you learn is that the energy of a classical harmonic oscillator is p squared plus x squared. You learn that the particle moves back and forth on the real axis, subject to Hooke's law, a spring force. It goes out to a turning point, it stops and turns around and goes back, goes to the other turning point, it stops and turns around and goes back, and it oscillates between these turning points. And you know that the turning point is at x equals plus or minus the square root of v, because that's where the particle is not moving, p equals 0. Okay, and you're also told in your course that there are classically allowed and classically forbidden regions. Okay, so this is the classically allowed region, and this and this, these are the classically forbidden regions. Why are they forbidden? Because if x is greater than the square root of e, then x squared is greater than e. But you can see that if x squared is greater than e, p squared must be negative. How could p squared possibly be negative? Okay, and in case you didn't understand that, here's a quick explanation of classically allowed and classically forbidden regions. This is it. Okay, you can see that. So, however, it turns out that argument is very weak and narrow. In fact, if p squared is negative, all that it says is that p is pure imaginary. So the particle can be here just so long as it's moving up or down into the complex plane. Okay, so if you put a particle over here, its velocity will be pure imaginary. It will go up into the complex plane and follow an orbit around here and go around a closed orbit in the complex plane. Okay, this orbit is actually an ellipse, and these turning points are the foci of the ellipse. Okay, so for the harmonic oscillator, its complex trajectories are ellipses, and this back and forth motion is just a degenerate ellipse. Okay, now, by the way, these orbits look like they're Keplerian orbits, but they're not, because as you know, Pluto takes a very long time to go around its orbit, whereas the Earth goes around much more quickly. In this case, for the case of the harmonic oscillator, all the orbits have exactly the same periods, okay, and that's by virtue of Cauchy's theorem. The period is a complex integral, and when you integrate around this closed path, you can deform it into any closed path you like, And therefore, all of the periods of all orbits are the same. Okay, so now we deform the harmonic oscillator by increasing epsilon from 0 to 1. And when you do that, these two turning points move down into the complex plane, and they're over here. And the classically allowed region consists of a particle trajectory going back and forth between the turning points in the complex plane, and all the other orbits, the ellipses, have deformed into these paths that look like this. Okay, so we have classical trajectories that are just the original trajectories, those nested ellipses, deformed into the complex plane. And now if we go to up to epsilon equals 2, the quartic case, we see that there's an interesting problem here. For this potential, classically, you know that on the real axis, classical particles roll down to infinity. Okay, they just roll off to infinity, either in the positive direction or the negative direction. And that's because you have an upside down potential. But here's a question for you. If you calculate the time for the particle to roll all the way off to infinity, it's finite. And it's just a simple integral. You can calculate it. Okay, and so it takes time t. So you can ask, where is the particle at t plus 1? And using real analysis, you can't answer that question. That's an example of an extremely difficult question in real variables, but one that's very easy to answer using complex variables. Okay, so here are the turning points. Here are the original turning points in the lower complex plane. There are also two more in the upper complex plane. Here is the classically allowed region. Here are the nested orbits that are the deformed ellipses. Okay, but now we can ask, can we analyze the system as a complex system? And it turns out it's very easy, because as you go closer and closer and closer to the real axis from the complex plane, you find that the orbit gets bigger and bigger and bigger, but it always takes the same amount of time to go from here and back as it does to go completely all the way around and back to where you started. And as you approach the real axis, what happens is that you go all the way off to infinity, you whiz around to the negative real axis and come right back up to the origin. Okay, so you can make a plot of the probability density for finding a classical particle on the real axis. And remember, this probability density gets small as the particle goes faster. So since it goes off to the complex, off to infinity very rapidly, the probability of it being found out here is very small. The probability of being near the origin is very large. So we have a localized probability of finding the particle near the origin. So although it looks like we have an unstable potential and the particle drifts off to infinity, in fact, it is most likely to find the particle in the vicinity of the origin, and complex variables tells you that the particle is actually in a bound state. Okay, so here is the picture in the complex plane. It's very likely to find the particle near the origin, and then it whizzes around extremely rapidly off at great distances. It's very unlikely to be found there, but it is very likely to be found right near the origin. Okay, so what you see here is that the static instability has become dynamically stable in the complex domain. And there are lots of physical examples where you have a static instability, but a dynamic stability. An example is a bicycle or a top, for just very simple example. Okay, and now you can quantize it. You could take those orbits and do an integral around the orbit of p dx and set it equal to n plus a half pi. And what you find is the quantum energy levels. And what you find is that the probability density of a quantum particle is not just spiked at the origin, but it has a bunch of wave-like probability, depending on which energy level it's in. It has many probability maxima. Okay. And so what you see is that the instability at x equals 0, the static instability, is tamed by doing a little bit of complex analysis. Complex analysis allows us to tame instabilities, and you can see that physical systems that seem to be unstable can actually become stable in the complex domain. Okay, so why is there no instability here? The answer is that if you extend the real numbers to the complex numbers, you keep almost everything about the real numbers. The laws of arithmetic, you know, the commutative law, the associative law, the distributive law, those remain the same for complex numbers as well as for real numbers. But you lose one thing. What you lose is the concept of greater than and less than. Okay, you lose the ordering property of the real numbers that the complex numbers no longer have. And so you can't use the words like unstable, because unstable actually refers to an inequality. You know, you say a physical system is unstable if it's if the potential is bounded below or not bounded below. Okay, but now you can't use those sorts of words, and so there are many physical systems that actually look unstable, but may actually be stable. Okay, so this is because you lose the notion of inequality in the complex domain. Okay, so let's go back to this picture I showed you before. Here are the eigenvalues, the discrete real eigenvalues for this Hamiltonian, where epsilon is real, and you can see that they're all very clearly defined. Okay, when epsilon is positive, they are real, but something happens when epsilon is negative. You can see that these two energy levels, when epsilon is negative, come together and become degenerate at this point for negative epsilon, and then they just disappear. And that is because those energy levels have become complex. Okay, so when epsilon is less than 0, some energy levels are real, but the rest of the energy levels are complex. But when epsilon is positive, they're all real. And so there's a transition that occurs at epsilon equals 0. This is called the PT transition. Okay, this is the region that we call the region of unbroken PT symmetry. This is the region of broken PT symmetry. In the region of unbroken PT symmetry, all of the eigenstates are also eigenstates of the PT operator. But in the region of broken PT symmetry, the states are not all eigenstates of the PT operator. The states of the Hamiltonian are not eigenstates of PT. Okay, so we have a transition. So we have a region of broken PT symmetry, a PT boundary, and a region of unbroken PT symmetry. And it's interesting that at the boundary, that's where the Hermitian Hamiltonians live. Okay, this is the case epsilon equals 0, where this Hamiltonian is Hermitian. But for all other values of epsilon, the Hamiltonian is not Hermitian. Okay, but it is still PT-symmetric. So Hermitian Hamiltonians live at the PT boundary, the PT transition. Okay, so just to tell you, I won't go into the details, but PT symmetry does not conflict with conventional quantum theory, but it is weaker. The condition of PT symmetry is much weaker than the condition of Hermiticity. All the eigenvalues of a Hermitian Hamiltonian are real, but for PT-symmetric Hamiltonians, only the secular equation is real. And unlike Hermitian Hamiltonians, there are two possibilities. PT-symmetric theories may have an all real or a partly real spectrum. If the spectrum is all real, we say we're in a region of unbroken PT symmetry. And if the spectrum is partly real and partly complex, then you're in a region of broken PT symmetry. So this is what you should remember. Here's an example of broken PT, and here's an example of unbroken PT. Okay. Hermitian Hamiltonians, in my opinion, are boring because the eigenvalues are always real and nothing interesting happens, okay? But PT-symmetric Hamiltonians are quite astonishing because there is this transition between parametric regions of broken and unbroken PT symmetry. And this is very easy to observe experimentally. Okay, so I'm going to give you an intuitive explanation of the PT transition. I want you to imagine a closed box with gain. Okay, so to describe this box, this is a quantum system. You're putting stuff into the system. Because stuff is going into the system, it's sort of like unradioactive, okay? It's, we have the opposite of radioactive decay. The state is growing in time. To describe such a system, you would use a non-Hermitian Hamiltonian. It's a 1-by-1 Hamiltonian because there's a complex number B in here. Depending on the sign of B, there can be growth or decay of the state. And here we have a state with gain, okay? Now, we can also add a box where stuff is leaking out of the box. We have radioactive decay here, okay? So here is a box where stuff is going in, and here is a box where stuff is going out. And now the Hamiltonian that describes this quantum system is a two-component, a 2-by-2 Hamiltonian, one with one sign of the imaginary part and one with the opposite sign. Okay, so by the way, of course, obviously, the system is not in equilibrium because this box is filling up and this box is leaking out. Okay, but we could now couple these two boxes with a coupling strength G, and now the Hamiltonian becomes this 2-by-2 Hamiltonian. So here's the box with gain, the box with loss, but they're coupled. And now it's possible for stuff to flow into this box and then flow forward into this box. And now what we see is that the Hamiltonian is not Hermitian, but it is PT-symmetric, and you can go home and check it. This Hamiltonian is invariant under combined time reversal, which is complex conjugation, and parity. Under parity, we simply exchange the two boxes. So parity is this 2-by-2 matrix, the parity operator, okay? So now, if you calculate the eigenvalues, they, again, just as before, they satisfy a real secular equation because it's PT-symmetric. And if you calculate the eigenvalues, you see that there's a transition when the coupling constant is equal to B. Okay, so you notice that the energy is real if G is bigger than B, but if G is small, then the energy levels are complex. Okay, so the system goes from having real eigenvalues to complex eigenvalues, and the system is in equilibrium for sufficiently large coupling. Okay, and that corresponds with the eigenvalues being real. Okay, and this is a simple example of the PT transition. So to put this in perspective, the PT-symmetric systems lie between closed and open systems, okay? Here is a closed system described by Hermitian Hamiltonian. Here is an open system described by a non-Hermitian Hamiltonian. But if the system is arranged so that the system is coupled to the outside world, it's not isolated, but stuff flows into the system and is balanced by stuff flowing out. That is, if loss and gain are balanced, then the system is invariant under PT-symmetry, under PT reflection. It's a PT-symmetric system described by a PT-symmetric Hamiltonian, and that's the kind of system that we're talking about here. It's a very interesting system, very easy to make in a laboratory, okay? So there's been lots and lots of work. There are, I don't know, close to 5,000 papers. In fact, there are probably more than 5,000 papers already published on PT-symmetric systems. These are just a few of the theoretical results, and there are also lots and lots of experimental studies of PT-symmetric systems. What I'm going to do for the rest of this talk is just show you a few pictures, just quickly visiting a few experimental systems, and then I'm going to say a few words about some theoretical results that maybe you'll find interesting. Okay, the main point to remember regarding theoretical studies is that renormalizing makes a Hamiltonian almost always into a Hermitian Hamiltonian into a non-Hermitian Hamiltonian. But it maintains the PT-symmetry of the Hamiltonian, and that explains a lot about the appearance of ghosts and runaway modes and things like this. Okay, so here is just here are a few examples of some of the experimental studies. The first observation of the PT transition using optical waveguides, I showed you a picture of that, and it was published in Physical Review Letters back in 2009. Here is a much better study of that PT transition, which was published in Nature. This is some work that was done in Shanghai and Rutgers on a PT-symmetric study of rubidium atoms. Okay, this is a study of non-reciprocal light propagations in a silicon photonic circuit. This is work done in Indiana on PT-symmetric superconducting wires. And again, you see the same picture that I showed you. Here is here we have two energy levels coming together and then becoming complex. This is a plot of the real energy level. Okay, so this is that study I showed you of PT-symmetry and spontaneous symmetry breaking in a microwave billiard. I showed you that earlier. This is a study done at Yale on PT-symmetric lasers and laser modes. This is a study of photonic lattices. These are exceptional points, study of exceptional points in lasers. Another study of photonic lattices here. A study done at Argonne, a more recent study on superconducting wires and PT-symmetry. This is work done in Beijing on PT-symmetric NMR. This is a more recent paper on PT-symmetric metasurfaces. Here's a study of PT-symmetric photonic crystals done in Stanford. This is a beautiful study. I won't take the time to describe it now, but if you're interested, ask me a question about it after my talk, because this is really cool stuff on wireless power transfer using a PT-symmetric circuit. Okay, and this is a beautiful elementary and very beautiful piece of work published in PhysRev. What they took was an electrical oscillator, just an LRC circuit here, coupled inductively to another LRC circuit over here. And so you have two oscillators, and now you can have one oscillator with loss. You just put a resistor in it so that it has loss, and you drive the other circuit inductively so that it has gain, and you couple them, and now you have a PT-symmetric system, and you can observe the PT transition. This is beautiful. When I saw this paper, I said, gee, maybe we could do it with another elementary system. Maybe we can just have two coupled pendulums. They're coupled because they're hanging from the same wire over here, okay? And we can have loss in one pendulum, resistive loss here. We can have gain over here, which is induced by an electromagnet up here. So we have a system, a coupled system with loss and gain. And once again, it becomes PT-symmetric, and you can observe the PT transition. So these are the equations of motion of the pendula. You have a pendulum here with loss, and it's coupled, the X pendulum is coupled to the Y pendulum. The Y pendulum is coupled to the X pendulum, and you can vary the coupling constant by varying the tension in the wire that the pendula are hanging from. Okay, and here's a very fancy experiment. This is an experiment using whispering gallery microcavities. Here you can have, here's a solid state device where you can have a light wave that goes around and around and around 1,000,000 times before it's absorbed. Okay, so this is called the whispering gallery. So these are two oscillators. You can couple them. You can have loss in one oscillator, just passive loss, and you can have gain in the other oscillator by just shining a laser beam on it. And once again, you can observe an optical PT transition. Beautiful piece of work. Okay, so here's an overview of my talk so far. Hopefully you're the people over here and not the guy over here. Okay, and so before I quit, I'm going to just mention in passing very quickly a couple of theoretical examples. So the first example is an old, beautiful, beautiful model, a field theory model called the Lie model. The Lie model was invented by Mr. Lie, T.D. Lie. It's a beautiful model because you can do renormalization, not perturbatively, but you can do renormalization in closed form. So the model is very simple. There's a particle that he called a V, which turns into an N and a theta, and then the N and the theta can recombine into the V. That's all. That's all that can happen. So this is like a proton going into a neutron and a pi plus, and then the same process in reverse. The Hamiltonian for the system is a free Hamiltonian, which simply counts up the number of N's and V's and thetas. And the interaction Hamiltonian says you create a V and you destroy an N and a theta, or you create an N and a theta and destroy a V. That's all. So T.D. Lie published this paper in 1954, but physics goes very fast. And in 1955, Shalane and Pauli published a paper saying, nope, this model is no good because when you renormalize it, the Hamiltonian becomes non-Hermitian and ghosts appear. Okay, so what they did was simply to calculate the renormalized coupling constant, which is what you measure in a laboratory, and they expressed the unrenormalized coupling constant G naught in terms of G. Okay, and it turns out, so you go to the laboratory and you measure G and you deduce the value of G naught, and what you find is that if G is larger than a certain critical value, G naught squared is negative. But if G naught squared is negative, G naught is imaginary. And if you look back at the Hamiltonian, if G naught here is imaginary, then the Hamiltonian is not Hermitian. Okay, that's a very serious problem. And if you've read Barton's book on advanced field theory, he says a non-Hermitian Hamiltonian is unacceptable, partly because it may lead to complex energy eigenvalues, but chiefly because it implies a non-unitary S matrix, which fails to conserve probability and makes a hash of the physical interpretation. And as I said before, renormalization creates instability. And this is a really hard problem. Pauli worked on it to try to fix this problem, and so did Heisenberg and Wick and Sudarshan. They all worked on it for a long time, but they didn't solve the problem. And for half a century, more than half a century, the Lie model was regarded as dead. It was not an acceptable physical model because it has ghosts. However, in fact, the model is PT-symmetric, and there's absolutely nothing wrong with the model. And so this is an example of ghost busting. PT-symmetry allows you to revive in unstable quantum theories that have become unstable because of renormalization that were thought to be dead. And if you're interested in that, you can read this paper that we wrote back in 2005. So there's another example I'll mention briefly. That involves the double scaling limit in quantum field theory. Double scaling limit is a correlated limit. It generates a universal theory in this correlated limit, which is an entire, the results are entire functions of a scaled variable, okay? But the double scaling limit of a conventional quartic theory, for example, has a problem, because in the double scaling limit, you wind up with a wrong sign quantum field theory. And you begin with a plus phi to the 4 theory, but after you take the correlated limit, you end up with a minus g phi to the 4 theory, where g is positive. And for many years, people thought that this was a serious fundamental problem with the theory, because the theory appears to be unbounded below. But no, as I explained to you before in quantum mechanics, there isn't a problem. And we've written several papers on this in case you're interested. Okay, so once again, PT quantum mechanics comes to the rescue. Two more brief examples, very, very brief. If you are interested in nonlinear differential equations, nonlinear differential equations have instabilities. A nice example of a system of a set of nonlinear differential equations are the Painlevé transcendents. These equations have fundamental instabilities that can be tamed and understood quantitatively by using PT-symmetric quantum theory. Okay, and here are some papers you can read if you're interested in this. Basically, Painlevé 1 has a basic instability. And to understand Painlevé 1, it turns out Painlevé 1, there are 6 Painlevés, but Painlevé 1 corresponds to this PT-symmetric Hamiltonian, the cubic Hamiltonian, which corresponds to epsilon equals 1. So do you remember that cubic PT-symmetric Hamiltonian I started out with? He doesn't, but this PT-symmetric Hamiltonian explains and gets rid of the instability of this nonlinear differential equation Painlevé 1. And by the way, Painlevé 2 corresponds to the PT-symmetric Hamiltonian with epsilon equals 2. So do you remember this quartic PT-symmetric upside down Hamiltonian? He is explaining to him how this works. This guy understands it very well. And Painlevé 4 is explained in terms of the sextic PT-symmetric Hamiltonian, which corresponds to epsilon equals 4. Okay, so one last example. How does PT-symmetric quantum field theory work? And I'll just say a few words about it before I quit, just very few words. You begin with a Euclidean quantum field theory. Let's take a theory in Euclidean space. We'll take a pseudoscalar field. So this pseudoscalar field changes sign under parity, but I changes sign under time reversal. So this is a PT-symmetric Lagrangian for a quantum field theory. And of course, the objective is to calculate things like the vacuum energy, the renormalized mass, the Green's functions as series in powers of epsilon, where epsilon is small. And we have a paper on this, a recent paper on this, which you can read if you're interested. Basically, to solve the theory, all you need to do is expand in epsilon for epsilon small, but you see something funny happening. The first term, when you expand this for small epsilon, the first term is, of course, just a free theory. But as you go to higher and higher powers of epsilon, you get more and more logarithms. So you need to make sense of this logarithm of I phi. And to do so, you interpret this logarithm term by saying if phi is positive, log of I phi has this form, but if phi is negative, it has this form. So combining these into a simple equation, you see that log of I phi can be written this way. Okay, so the imaginary term is odd in phi, the real term is even in phi, and that is how we ensure the PT-symmetry of the Hamiltonian or the Lagrangian. And now this is just the answer. I'm not going to explain to you how you get it, but this is the endpoint Green's function for all n except for n equals 2. I'll show you n equals 2 in a second. But for all n except for n equals 2, this is the exact answer to order epsilon. Okay, the exact answer. Where delta here is the free propagator in coordinate space, so it's a Bessel function. And you notice that delta of 0 has this form, and you can see this becomes infinite at d equals 2. So you have to do renormalization as soon as the dimension of space, of Euclidean space, reaches 2. So if you calculate the 2-point function and you go to momentum space, you see it has this form. And if you look at the pole of the propagator, that's the renormalized mass. And it's very nice. You can see the renormalized mass is real, but you can see the renormalized mass becomes infinite. It becomes logarithmically divergent at d equals 2, because you have here a delta of 0. And you need to renormalize the theory. And you renormalize the theory by putting counter terms in the Lagrangian. We are writing a paper on this right now. I hope it will go on the web in the next couple of weeks or so. We've been doing very detailed calculations, and it looks like we can renormalize the theory order by order in powers of epsilon. Okay, so thank you very much for listening to my talk, and I'm very happy to answer questions in case you have any.
Yeah, thank you very much for the talk. Do we have questions?
Yeah, probably, I don't know. Do you hear me? I can probably start? Okay, I just, so I can be seen. I'm Carl Lastana. Okay, yeah, I have a couple of questions. And the first one is, in one of your example Hamiltonians was just the x to the 6 potential.
Yes.
Now, usually I wouldn't invoke PT-symmetry for solving this. So does a PT treatment of this give a different result, or is it completely equivalent to it?
Yes, it does. Yes, it definitely does. So what you're talking about is the Hamiltonian, is the sextic Hamiltonian, which corresponds to epsilon equals 4. And this is the Hamiltonian p squared plus x to the 6th. Okay, so remember that an eigenvalue problem consists of 2 parts. Just in a standard simple eigenvalue problem, it consists of a differential equation and boundary conditions. Okay, if we begin with epsilon equals 0 and we do an analytic continuation to epsilon equals 4, you do not get the conventional p squared plus x to the 6th theory. So you know all about the p squared plus x to the 6th theory, and the boundary conditions here are that the eigenfunction must vanish as x goes to plus or minus infinity. That's the conventional quantum mechanical x to the 6th theory. However, as you increase epsilon from 0 to 4, the boundary conditions on the wave function are different. The boundary conditions, I can go into greater detail, but the boundary conditions are always imposed in Stokes sectors in the complex plane, and those Stokes sectors rotate. So we have these Stokes sectors, which include the real axis when we begin at epsilon equals 0, but they rotate down in the complex plane off the real axis. Okay, so the boundary conditions now are different boundary conditions. It's the same differential equation, but different boundary conditions. and the eigenvalues are not the same. They're real, but they're not the same real eigenvalues that you would study in a simple elementary quantum mechanics course. They're different. Okay, so that's because they are imposed in different Stokes wedges, just discretely different Stokes wedges, and that's pretty much the trick of this whole business. The fact that the complex plane is deeply involved in the calculation here. Okay, now I can go into greater detail if you like. I can maybe draw some pictures for you. But yeah, maybe let me actually, I can try. Let's see. Yeah. Okay. So so for the harmonic oscillator, we have two 90-degree opening Stokes wedges. This is for the harmonic oscillator. Here is the real axis. Okay. And if you're studying just the harmonic oscillator, as you go to plus infinity and minus infinity, the eigenfunctions are supposed to vanish exponentially fast. In fact, they continue to vanish exponentially fast in this Stokes wedge, which has an opening of 90 degrees here and 90 degrees here. As you analytically continue in epsilon, what happens is that this Stokes wedge moves downward, it rotates downward, and this Stokes wedge rotates downward into the complex plane. So what you get, here's the complex plane, and now the Stokes wedges have gotten thinner and they have rotated downward into the complex plane. So the eigenfunctions have to vanish in this Stokes wedge here, and they have to vanish in this Stokes wedge here. And the quantization path looks like this. Of course, the Stokes wedge is only an asymptotic concept. So you can follow the real axis as long as you like. But as you go off to infinity, you have to go off to infinity that way and that way. Okay. And so instead of going to infinity along the real axis, you have to go to infinity at great distances in the complex plane, and that gives you a completely different theory. Okay, so the theory that is defined by analytic continuation is not the standard theory that you would naively work on in an elementary quantum mechanics class. Okay, but both theories have real positive spectra. They both theories have bound states. They're both stable theories, and so on. Okay, is that?
Yeah. Okay.
Mm-hmm.
Okay.
There are some questions in the
okay.
So Carl, maybe I can take. There's a question from one of my students in the chat. Marcus is asking if you deformed a non-Hermitian or Hermitian system to a PT system and then find some result, can you deform that result back?
I didn't quite understand that. You said if you deform a non-Hermitian system, I wouldn't do that. In other words, if you pick a random non-Hermitian system, the system that you're talking about typically is a system that is coupled to the outside world, and the gain and the loss are not necessarily balanced. So that is a fundamentally non-Hermitian system that has complex eigenvalues because it is growing or decaying in time. And there's no point in starting with a system like that and analytically continuing it, because it's a system that is inherently non-Hermitian. However, what I always do is begin with a Hermitian system and then deform that system into the complex plane, immediately losing hermiticity, but maintaining PT-symmetry, so that you always you begin with a system that has no loss and no gain. And as you analytically continue it, its net loss and gain the net loss and gain is still zero, but now the system can have gain and can have loss, but they're balanced. Okay, and so I mean, naively, you can understand, for example, a minus x to the 4 potential as a balanced loss and gain system, because particles are coming in from minus, they're coming up from minus infinity, okay, but they're going out at plus infinity, okay, and they're not getting lost anywhere in the middle, so we have a balanced loss and gain, okay? So in this case, the eigenvalues actually remain real, okay? And the condition, I won't explain this because this is a more detailed statement, but the condition that the eigenvalues, if you have some sort of potential, if you have some sort of potential that looks like this, okay, just some sort of potential, maybe this is unbounded below it. It's a potential that goes down to minus infinity. Okay. And you have an incoming wave over here. When it encounters this potential, typically there is a reflected wave, okay, and there's a transmitted wave, okay. Now, PT symmetry occurs when there is zero reflected wave, okay. So it involves a reflectionless potential. So you have an incoming wave and an outgoing wave of the same magnitude, but no reflected wave. Okay, and that's the quantization condition that gives you the eigenvalues for example, for a minus x to the 4 potential. And that condition arises naturally when you do an analytic continuation for complex epsilon. Okay, this is not at all obvious, but that is the underlying explanation of PT symmetry. Okay, that gets mathematically technical. Okay, but that is what is happening. So when you have a reflectionless potential, and this happens in the case of lasers, when you have a PT-symmetric laser, what happens is that it becomes, you can have a one-way laser. You can have what is called unidirectional invisibility. Okay, so when the light goes one way, you don't have any reflection. Okay, you can be invisible when the light goes one way, but not when it goes the other way. It's very, very interesting.
Okay, thank you. Maybe I can try to interpret what Marcus was saying. So I think you probably answered his question, but maybe his question also had the part, like if you had a non-Hermitian system, like a truly non-Hermitian operator which has complex eigenvalues, like that's a hard problem in general to solve and to understand what it means, I guess. So maybe I can rephrase the question: can you find the like a mirror image to that system where like the gain of that system that you then would couple would balance the loss of that non-Hermitian system and learn something about, because more or less that's what you've done, no?
Yes, yes, indeed, that's right. So in general, what we can do, you're in this case, you're absolutely right. Let me see, I think I can. Yeah. Okay. So so what I can do is I can take a system over here, which is, as you say, sort of a true non-Hermitian system. For example, it might be some sort of radioactive system here where particles are coming out of the system. and it's definitely non-Hermitian. I mean, we can't describe this system with a Hermitian system because it's losing particles. Probability is not conserved. Okay, but what we can do is we can then construct a mathematical brother to it here, where it is going backward in time, if you like, where it is where stuff is going into the system. So this system has gain, this system has loss, and this system taken as a whole is now by construction PT-symmetric. Okay, where T just refers to time reversal, and P, parity, refers to the interchange of this system and this system. Okay, so P is an operator that simply interchanges the two components. T is time reversal, the usual notion of time reversal. And you can see that the system is invariant because if we interchange the two systems physically, but we also have time backwards, to time flowing backwards, so loss becomes gain and gain becomes loss. Now the system has PT invariance, okay? And taken as a whole, the system there are two possibilities for the system. It may still have still have complex eigenvalues, or it may have real eigenvalues. And to make sure that it has real eigenvalues, all we need to do is to couple the two systems together with a coupling constant. And if that coupling constant is strong enough, then there's enough internal flow so that the system can be balanced. Okay, so I mean, there are lots and lots of systems that have a phase transition, and that phase transition is a critical point where the system goes from being having an unbroken PT symmetry with real eigenvalues to a broken PT symmetry. And indeed, I mean, we can talk about this in great detail. You know, maybe the Hamiltonian for the universe, you know, I mean, we can have decay and undecay, and we can discuss the possibility that the Hamiltonian for the universe is PT-symmetric because part of it, you know, maybe part of the universe is falling into a black hole and part of it is coming out in the form of Hawking radiation, and it may be in balance. And, you know, I mean, there's all kinds of interesting dynamics that you could consider here. But this is the basic idea of a PT-symmetric system. Okay.
Okay, great, thank you. Without knowing it, I think I asked one of the questions that we had in the chat. Let me just spell out the question from Blaise Gautreau, just in case there's a facet that you would like to add, because this question was a bit more specific than mine.
Yeah.
So what about spectra like we have in holography, where eigenvalues, in our case, those are quasi-normal mode frequencies, complex quasi-normal mode frequencies of fluctuations around black holes, where they can be purely imaginary. Some of them are, right? And then in contrast to the spectra that you were mentioning, which are purely real or partly real, does PT-symmetry have anything to say, non-trivial to say, about the situation where you can have purely imaginary eigenvalues?
Yeah, sure. So, of course, I can imagine some Hamiltonian whose eigenvalues are pure imaginary. And clearly, if I multiply by that Hamiltonian by I, its eigenvalues will be purely real. Okay. And so whether or not the Hamiltonian is Hermitian, if the eigenvalues are purely real, then that system actually has a PT symmetry, whether or not P is actually space reflection and T is actually time reversal. T is simply an antilinear symmetry, And P, in some generalized sense, P is some linear symmetry, okay? And typically it's a Hermitian operator. And that system has a symmetry. In fact, I will tell you just in complete generality, I didn't go into the mathematical details, but very, very simply, if you have a PT-symmetric Hamiltonian and you find by calculation, or you can do a computer study, it doesn't matter, or by analytical proof, if you can show that the eigenvalues are entirely real, or if you multiply the Hamiltonian by I so that the Hamiltonian has entirely pure imaginary eigenvalues, if you can show that, then what you can show is that the Hamiltonian has a secret symmetry. It doesn't just have PT-symmetry, it has a completely independent linear symmetry operator, a discrete symmetry operator, which I would like to call C. And C also commutes with the Hamiltonian. Okay, so it's a secret symmetry. It's not trivial to actually calculate that symmetry operator in closed form. It can be done in some systems, but not explicit, not exactly. It can be done approximately, but there's an operator C, okay? And this is, as you can see, this is like the CPT theorem. So the Hamiltonian not only commutes with PT, but it commutes with C, where C is a linear operator, having the property that C squared is 1. So it's like charge conjugation, okay? And the product of CPT is crucial here, because although the Hamiltonian is not Hermitian, at least formally, it is self-adjoint with respect to CPT. Okay, so if you have a Hamiltonian whose spectrum is purely real, or in your case, pure imaginary, so the Hamiltonian we're discussing is I times H, okay, there is an operator called CPT, and C commutes with PT, and C squared is 1, and PT squared is 1, okay, and the Hamiltonian is self-adjoint if it's in an unbroken PT-symmetric phase, so all the eigenvalues are pure real or pure imaginary in your case, then that Hamiltonian is formally self-adjoint. It's not Hermitian, so it's not, it doesn't go into itself under direct conjugation, but it does go into itself under CPT conjugation. That is, CPT applied to that Hamiltonian gives back that Hamiltonian. CPT times H times CPT inverse gives back H. Okay, so that's a beautiful result, and that is a generic property of what happens in the unbroken region. In the broken region, there is no C operator that you can construct. And if you try to construct one, what you find is very strange things, okay? What you find is that now the CPT inner product, the CPT norm, has, you find that complex conjugate eigenvalues correspond to states that have 0 norm. Okay, but that 2 complex conjugate states dotted together have norm 1. So it's exactly the opposite of what happens in a conventional Hilbert space. In a conventional Hilbert space, 2 states dotted together give you 1, but a state dotted to another state, you know, if they're different, correspond to different eigenvalues, gives you 0. Okay, they're orthogonal. Okay, this is so you have an orthogonal basis. But in the broken PT-symmetric region, you have self-orthogonal states. The state corresponding to a given energy is orthogonal to itself. Whereas if you take the energy and its complex conjugate energy, that state dotted with itself gives you 1. So it's a very strange result, and a lot more work needs to be done mathematically to understand what is going on. So far, it's an open problem, and lots of mathematical work needs to be done to understand what's going on there.
Thank you. Yeah. I think.
Can I make a comment probably?
Yeah, Carl, you
just into the direction of holography, because we recently, and shamelessly, I posted it in the chat. So I'm switching my video. We recently worked out a holographic model which implements this PT-symmetry, and we pretty much find all these beautiful properties we have learned today. So there's this PT phase transition and then all these things.
That's great. That's really, really nice.
Yeah, but so it works out exactly what you think. And beyond the phase transition, for example, you don't find real solutions anymore. You find a pair of complex conjugate solutions and so on. And the key point to this is, which is slightly different from what we are used to in holography. In holography, for computing quasi-normal modes, you impose non-Hermitian boundary conditions on the horizon, these infinite boundary conditions. Now, for really constructing a PT-symmetric holographic system, you have to impose these non-Hermitian boundary conditions actually on the boundary, such that you model a Hamiltonian of the dual system, which has this PT non-Hermitian couplings. Okay, so sorry for this promotion of that.
No, that's great. That's wonderful. That sounds like really great work. I mean, the PT transition occurs in all sorts of examples. It occurs. I mean, systems that you know and have studied long ago are systems that are PT-symmetric. The Korteweg-de Vries equation is PT-symmetric. All sorts of if you studied fluid mechanics, there are lots of fluid mechanical systems that are PT-symmetric. Virtually every nonlinear wave equation that you've studied, the 3-wave equation, all sorts of the nonlinear Schrödinger equation, they're all PT-symmetric systems. They are non-Hermitian, but they're often PT-symmetric. And in fluid mechanics, there are lots of transitions that you study that are, in fact, PT transitions. There was just a paper on, for example, the Rayleigh instability. You know what that is? In the Rayleigh instability has to do with the formation of thunderclouds. You know, you have hot air close to the Earth, cold air above. The hot air punches. This is an unstable system, and you have the formation of thunderclouds as the hot air penetrates through the cold air, and that transition is known as the Rayleigh transition, and it's called the Rayleigh instability. That is a PT transition, okay, where eigenvalues go from being real to being complex, okay, and when they're complex, you see a growth of the thunderclouds, okay. I mean, it's PT, the concept of a PT transition and a PT instability and so on. It occurs everywhere, all over, in so many systems. All the systems that you've studied throughout your entire education. Whenever you come across a transition, you see something like that.
Can I make one more question and then I shut up? I promise.
Oh, don't. I like the first comment very much.
Okay, so since this PT-symmetric Hamiltonians, they are always sort of open quantum system, which with a balanced gain-loss property. Now, if one looks up, quantum mechanics of open systems, one ends up with studying something like the Lindbladian. Is there any relation? Can one understand this PT Hamiltonians as sort of special forms of Lindblad equation, Lindbladians, which implement this balanced gain loss?
Yeah. Okay. So let me say, first of all, I have not done any work on the Lindblad equation. However, the answer to your question is yes. People have begun studying PT-symmetric systems via the Lindblad equation. One of my, in fact, several of my long-term collaborators have worked on it. You can find some recent papers on the Lindblad equation and PT-symmetry. If you just do a search on the web for my collaborator, whose name is, he's in London. His name is Dorja Brody, and you can see some work just in the last year. He's put some papers on the web on that, and I would recommend that you look at those papers, okay? Because that's your question is a very good one, and it's a very natural thing to do, to study such systems using the Lindblad equation, and indeed that's exactly what Dorja Brody has done, and that opens a whole enormous possible area for research that you could, I mean, the limits on that seem to be endless. I mean, the work that you could do is unbounded, and that just in that area, because it's just been, the idea has just been examined. It's only a year or so old, and indeed you should look into it, because I'm sure you'll find something very rich and interesting to study.
Okay, thank you very much. Thanks for this beautiful talk as well.
Mm-hmm.
Okay, thank you. So.
Okay, I think these are all the questions that we had, unless somebody speaks up. We also, if Carl agrees, then we have like a minute or so. I mean, this was an extended discussion session, so I'd like to let everyone go and stop the recording, and then we have, off the books, we have another 2 minutes maybe, if there's anything somebody wants to ask. So let me just stop the recording here. And first of all, thanks, Carl, again for the very clear talk and for your long discussion session. Thank you very much.
Yeah, it's my pleasure.